This programme is about settled sewerage, sometimes called small bore sewerage. And the first reference to this is in a book published in England in 1935, which said, if there's not enough fall to give a self-cleansing velocity in the main drain, it will sometimes be possible to put in a septic tank at the head of it. The effluent from a septic tank, being free from any solids capable of choking a drain, may be safely laid with a merely nominal fall. The first report of an actual settled sewerage scheme was published in 1961, and this described sewered aqua privies in what was then northern Rhodesia, now Zambia, and this was followed in the mid to late 1960s by a scheme in New Busa in Nigeria. The sewered aqua privies in northern Rhodesia were first installed in 1960 at Kafui Flats, about 50 kilometres south of Lusaka, and the site gradient was very flat, 1 in 2,000. This was the first sewered aqua privy system, and the settled sewers were designed for a self-cleansing velocity of 0.3 metres per second. And the scheme used 100 millimetre diameter sewers laid at a gradient of 1 in 200. And the wastewater was treated, at least initially, in a series of waste stabilisation ponds. This slide shows a typical layout of an aqua privy block as used in Zambia. There are 4 units shown at the top, 1 for each of 4 houses, and they sit above a common watertight tank which lies underneath them. This slide shows the 4-unit aqua privy block and the 4 houses it serves. It also shows how the aqua privy effluent is discharged into a 100 millimetre diameter sewer, and this discharges in turn into a street sewer of 150 millimetres diameter. In the mid to late 1960s, sewered aqua privies were installed in the resettlement town of New Busa in Nigeria. There were 256 compounds, each serving an extended family of something between 15 and 40 people. Each compound had a sanitation block with an aqua privy, a laundry area and a shower, with a water tap in the laundry area. Solage was discharged into the aqua privy tank, and so it's sometimes described as a self-topping aqua privy. There was no information on the hydraulic design of the system, and we presume it to be the same as in Zambia. A 100 millimetre diameter compound connection to a lane junction box, and then a 150 millimetre diameter lane sewer with treatment in waste stabilisation ponds. Aqua privies are now a questionable sanitation technology. They require an expensive watertight tank, they have a fairly crude drop pipe, and it's difficult to maintain the water seal. And pour flush toilets are really much less expensive and also more sophisticated, at least to the users. But sewered aqua privies gave us settled sewerage, first installed in Zambia in 1960, then in Australia in 1962, Nigeria 1965, in the United States in 1975, in Colombia in the very early 1980s, and in South Africa in 1990. This slide shows the basic components of a settled sewerage scheme. A house or a group of neighbouring houses discharge their wastewater into an interceptor tank, which is basically a single compartment septic tank. In the tank, the settleable solids settle, and the solids-free effluent is then discharged into the settled sewer running outside. Clearly, settled sewerage is really very appropriate in areas which already have septic tanks, as the cost then is much less. Now we move to the design of settled sewers. And the first thing we have to establish is the peak flow per household in litres per second. And this is equal to K1 times K2 PW divided by 86,400. K1 is the peak factor. In the United States, they've observed values of the peak factor of between 1.2 and 1.3, but for design purposes, we would normally use 1.5. K2 is the return factor, that is to say the percentage of water consumption which ends up as wastewater, and that's usually between 80 and 90%, and so we would use a K2 value for design of 0.85. P is the household size, the number of people in the household. W is their water consumption in litres per person per day, and 86,400 is the number of seconds in a day. So using those values for K1 and K2, the peak flow per household is 1.5 times 10 to the minus 5 times PW. A really important feature of settled sewers is that the flow can be either open channel flow, that is to say with a free water surface, or in sections of the sewer which lie below the hydraulic gradient, full bore pressure flow. And we make a separate analysis for each section of sewer in which the type of flow, either open channel or pressure flow, does not vary, and over which the hydraulic gradient is reasonably uniform. The basic equation we use for the design of settled sewers is Manning's equation. This states that the velocity of flow in meters per second is equal to 1 over n times r to the power 2 over 3 times I to the power 1 over 2. N is Manning's pipe roughness coefficient. It's dimensionless and has a value normally of 0.013. R is the hydraulic radius, that is to say the area of flow divided by the wetted perimeter, so it has units of meters. And I is the sewer gradient in meters per meter, so dimensionless. Strictly speaking, it's the hydraulic gradient. When the sewer is flowing just full, little r, the hydraulic gradient, equals big R, the hydraulic gradient at full flow. And big R is given by pi d squared over 4, where d is the sewer diameter in meters, divided by pi d, and that's equal to d over 4. Now velocity is equal to flow over area, so Manning's flow equation becomes q equals 24d to the power 8 over 3 times I to the power 1/2, when d is in meters. Or when d is in millimeters, q equals 2.4 times 10 to the minus 4, d to the 8 over 3, I to the half. In these sorts of hydraulic calculations, we always have to be very, very careful with units. Now, the basic design concept is that the value of Q given by this equation has to be greater than the estimated peak flow in the section of sewer which we're designing. If not, then we have to use the next larger available pipe diameter. Workers in the United States developed for settled sewerage the inflective gradient design approach. In this design procedure, the sewer profile closely follows the ground profile so that flow conditions change as required from open channel flow to pressure flow and back to open channel flow and so on. And this method was the first method to realize that a self-cleansing velocity in settled sewer was not required, as the sewer only conveys settled wastewater, so all the solids have been retained in the interceptor tank. There are two things that the design has to ensure. Firstly, that there is an overall fall across the whole system, and secondly, that the hydraulic grade line does not rise above the level of the invert of the outlet of any interceptor tank. Otherwise, wastewater would flow from the sewer back into the interceptor tank and cause local flooding. In relation to the second point, we have to consider critical points where we establish the maximum sewer elevation. And the critical points are high points where the flow changes from open channel flow to pressure flow, and points at the end of long flat sections.